Well, hello, Algebra 2 students. I'm sad that I am not with you again this week, but we are going to do the very best that we can, even without being able to see each other face to face. I hope that these videos are at least helpful there in class and that you guys are doing all very well. And so we're going to jump into this together. We're going to be looking at section 7.1, talking about radicals in this chapter. So just to get us started, we have a couple of quick warm-ups. Let's see if you guys can do these. What's the square root of 441? Well, you know it's more than 20, right? It's 21. All right, what about the cube root of 216? So what times itself 3 times gets us to 216? We know that 4 times 4 would be 16 times 4 would be 64. That's not enough. 5 times 5 would be 25 times 5 would be 125. So maybe 6? Yeah, it's 6. And then what about this one, the square root of 0.0004? That is 0.02. All right, so for any real numbers a and b and any positive integer n, if a to the n equals b, then a is an nth root of b. The radical sign indicates a root. And the expression under a radical sign is called the radicand. So let me kind of show you that. So this is what it looks like. We have, whenever we're dealing with a root, you see the radical sign is that, is this symbol here. That's the radical sign. The index is the n here in this equation, and then the b stands for the radicand. So if I say the radicand, that's the thing that's underneath the root symbol. The root symbol is also called the radical sign, and then the index is how many roots we're taking of a particular radicand. Now, when n is even, the radical sign indicates the non-negative or principal root. So here, this chart is actually included also in your book, where it has real nth roots of b. So the radicand here is, again, our symbol b stands for that. So this is talking about the case where the stuff underneath the radical, the b there, value, the radicand, is greater than 0. So it's a positive number. Well, if it's a positive number and the root that we're taking is even, it's 2, 4, 6, 8, that kind of thing, then we're going to get one positive and one negative root for that thing. Again, if it was like, for example, the square root of 4, then both plus and minus 2 would satisfy that. Negative 2 times negative 2 gives us 4, just as 2 times 2 gives us 4. If, though, this is an odd value, let's say that it was the cube root of 8, then obviously the answer is only a positive number. It's 2 times 2 times 2 gives us 8. Now, if the b value is 0, if we have a 0 under here, then whether it's even or odd, we're only going to get one answer, and it's going to be 0. The root will be 0 no matter what. Now, if the b value, though, is less than 0, in other words, if it's negative, let's say this was a negative 8. Well, if we're taking the cube root of negative 8, then negative 2 times negative 2 times negative 2 does give us negative 8. So we're going to get one negative answer if it's a negative value under there and the n value is odd. Now, if it's even, though, if we have, like, for example, a square root of negative 4, so that's a b value that's less than 0. It's now, the second root, otherwise known as the square root. Recognize here, we don't have a real root. It would involve here an answer like 2i. We could do plus or minus 2i. That's an imaginary number. That's a complex number, not a real root. So that's why here it's saying there's no real roots. If the b value is negative, the radicand is negative, and the root amount is an even number. So let's talk about product properties of radicals. If we have two roots, here the nth root of x and the nth root of y, and they're real numbers, then the nth root of xy equals the nth root of x times the nth root of y. You can take the roots individually and then multiply their answers together, or you can multiply them both together if they have the same, again, this is the same root value here, if the same index number, then you can multiply them together first and then take the nth root of their product. Okay, so let's take an example like this one. Simplify the third root of 8x cubed y to the 12th. Well, we could rewrite that expression this way, couldn't we? Where it's 2 to the third, x to the third, and y to the fourth to the third. Notice that whenever you have an exponent raised to another exponent, this 4 times 3 would be 12. Now, the reason we do that, so now we can now take each of those values and just put it as 2 over 3, 2 to the third over 3. X, we do these separately, 3 over 3. Y to the fourth raised to the 3 over 3. And notice that each of these just become 1. These 3 over 3 is just 1. And we just get 2 times x times y to the fourth. Now, if you like to do it this way, then that might be helpful. Instead, you might just right here from the get-go, just distribute this 3 and make it 1/3. So 8 to the 1/3, x to the 3 over 3, and then y to the 12 over 3. I think actually this is a little bit simpler. So now we're just taking the third root of 8, which you just need to know is 2. 2 times 2 times 2 is 8. X to the 3 over 3 is just x. Y to the 12 over 3, reducing that to just be to the fourth. So again, either way works. How about this one? The fourth root of 81, a to the 16th, b to the 8th. Remember here, the fourth root of 81, we'll see 2 times 2 would be 4, times 2 is 8, times 2 is 16, so it's not that. 4 times 4, we'll see 3 times 3 would be 9, times 3 is 27, times 3 is 81. So it's going to be 3 is the fourth root of 81. And then a, 16 divided by 4, you just put that, whatever is out here, you put underneath these guys instead. And so then that just becomes 16 divided by 4, which would be just a to the fourth. And then b to the 8 over 4 would just be 8b squared. So again, working out another way, you could show this as 3 to the fourth, a to the fourth raised to the fourth, b to the second raised to the fourth, and then divide all those 4s. You see the 4s all cancel out with one another, and you get 3a to the fourth b squared. Okay, notice this one. Simplifying square root of -9c to the 12th. Remember, if there's no index value here, it's a square root, which means there's a little 2. So what's the square root of -9? Well, you should instantly recognize that this is a problem. It has no real roots because you can't take the square root of a negative number. Remember, you can't ever take an even root of a negative number in the radicand. This radicand is negative, the index is even, therefore we have an imaginary root. So if we were going to complete this, it would be 3, that the square root of 9 is 3, but we would write 3i, because remember this I stands for the square root of -1. That's the imaginary number. So we could rewrite this as 3i and then c to the 12 over 2, which is 6, which is that answer. Okay, so the nth root of x to the n, or nth root of x to the n, is the absolute value of x if n is even. And it's just x if n is odd. Again, this makes sense, right? If we take the square root of x squared, we've already learned together that that is just the absolute value of x. It'll always give us back a positive value for x. But if we take the, let's say, cube root of x cubed, the answer to that is just x. Because if this is -3, then you'll get back a -3. If it's a +3, you get back a +3. But in this case, even the negative number will become positive. So that's why whenever there's an even root situation, it always yields us an absolute value. If it's an odd number on the index, then it just yields us the number itself. So simplify this one, the negative square root of 49y squared z to the 12th. Well, we would take the square root of 49, and we'd notice that that is 7 squared. And notice here y squared z to the 6th squared. And now we just take that square root into everything. And we're just left with -7. Notice that the y here is being shown as an absolute value of y. And that's because we have that very specific case of the square root of y squared. So technically, that's the absolute value of y times z to the 6th. Now, if we simplify on this guy, the cube root of 192, a to the 5th, b to the 10th, again, this is a case where I think that we can split this into a couple of different ways. You can show this 192 is actually 2 to the 6th power, and 2 to the 6th power times 3. So if we were going to do kind of a tree structure, you do a factor tree on this. You can just keep dividing this by 2, and you'll divide it 6 times that way, and then you'll have it also with a 3 at the end of all of that. So you have 2 to the 6th times 3, and then if further split this a to the 5th, we can also rewrite a to the 5th as a cubed times a squared. Remember, whenever we multiply the same bases with different exponents, we just add their exponents together. So 3 plus 2 would equal 5. So we can rewrite that a to the 5th as a cubed a squared. We can do the same thing here with b to the 10th. We'll find something that gives us multiples of 3. So if we can rewrite that as b to the 9th, b to the 1st. Remember, when there's the 1st, we don't have to write the little 1 there, but I'll do it here just so you remember that's what that is. So it would be 9 plus 1 is 10, and that's why we still have an equivalent expression here. And then we just take the cube root of each of these parts. So the first one, you would separate these out into different pieces. Notice this last part is just the parts of the a squared, the a and the b and the 3 that don't have the nice multiples of 3 in them. And then on the other guys, we just go ahead and with all these exponents, we're going to divide those 3's by 3 from this radical, and then we can get rid of these radical signs, and we're just left with 2 squared ab cubed times the cube root of 3a squared b. 2 squared is obviously 4, so that's just 4ab cubed times the cube root of 3a squared b. How about this one? Simplifying, taking the 4th root of 32x to the 5th y to the 7th. Again, so here we have 2 squared would be 4 times 2 is 8 times 2 is 16. So that'd be 2 to the 4th is 16. And then we have an additional 2 left. So we could rewrite that way. We could write this x as x to the 4th with an additional x, and then the y to the 4th with an additional y cubed, right? And that way we've got all of our guys there. We can then, we're taking the 4th root of all of this. So on this first guy, the 2 to the 4th over 4 is just 2. The x to the 4th over 4 would just be x. Same thing with the y. Y to the 4th over 4 would just be y. And then we have to keep the 4th root of the stuff that didn't fit under that. So it would be the 2. We would have an x left over and a y cubed. And that should be our answer. Again, we'll work it over here. Notice it's 2 to the 4th times 2 times x squared, x to the 4th times x, y to the 4th times y to the cubed. Oh, and I did leave out, so whenever we're taking the square root or the 4th root of something to the 4th, we also actually have to put the absolute value on that value. And then we have the 4th root of 2xy cubed. Okay, now, Herons Formula is a really interesting one. What Herons Formula allows us to do is to calculate the area of a triangle whose side lengths A, B, and C are as follows. So the area equals the square root of the semiperimeter times the semiperimeter minus A times the semiperimeter minus B times the semiperimeter minus C. So that S equals the lengths of all the sides divided by 2. So in other words, half the perimeter of the entire triangle. So wherever we have S in this formula, we are just plugging in the answer to this. A plus B plus C divided by 2. So half of the total distance around the triangle is what the S stands for. And what's cool about this you've learned a long time ago, I'm sure, in geometry or even maybe algebra before that, the area of a triangle is 1/2 base times height. And that works out really well if you have a triangle that's a right triangle where you have the height of it and you have the base of it, where the base and the height are obvious like this. Or if you have a triangle like this, but you're provided with the height of the triangle, then that works. But what happens if you have a triangle, it looks like this, and you just have values of sides, and this is not a right angle sitting in here? Then what do? Well, you can use Herons Formula, where you just add these 3 sides together, divide it by 2, that gives you the S value, and then you just plug in for S where it goes here, and then you plug in for the 3 side lengths that you have. So let's look at an example of doing that. So find the area of a plot of land. So this plot of land has an 81-yard side, has a 54-yard side, and a 45-yard side. And we don't know what this angle is. Well, what's great about Herons Formula is it doesn't matter. We don't need to know the amount of these angles in the triangle at all. We just need to know the lengths of the sides. So we just plug these in. 81 plus 54 plus 45, all divided by 2. Yields us 180 divided by 2, or 90. And then we're going to plug all of that information into the longer formula for Herons Formula. So 90 times 90 minus 81 times 90 minus 54 times 90 minus 45. And when we get that, we take 90 times 9 times 36 times 45, which we could, in order to keep it as an exact number, we could, again, find which one of these values. We could factor these into a factor tree and figure out which things are squared and which are not. And if you do that, you eventually get to an answer that looks like this. And eventually we get to the answer of 810 square roots of 2 yards squared. Or if you put it in the calculator, which I would be completely fine with in general, you would need to do all of that extra work. 1,146 yards squared would be the answer for the area of this triangle. So Herons Formula is really useful. If you have a triangular plot of land, you can calculate the area just by using this formula. Really, really great. All right. Well, that concludes my look at section 7.1 with you guys. Your assignment is to look at pages 290 through 292 and to do numbers 2 through 40 and 60 through 68 even. Those 60 through 68 ones, again, are obviously the cumulative review ones, which kind of review things that you've already done. But these are the new problems that you'll be working on. I don't think you'll find these to be all that difficult. I think the first couple sections of this chapter should be a little bit of review for you. So hopefully this won't be that difficult. But let me know if you guys have any questions or need any additional help. I hope you guys are doing well.